So is my screen visible to all of you?
Yeah,
Okay. Okay, so good afternoon all. Today we are going to discuss about the week 6 lecture. So uh, about the introductory organic chemistry second, which is a NPTEL course, which is a NPTEL platform course. So you can find the videos on the NPTEL platform. So the course instructors are Professor Harinath Chakrapani and Professor Neeraja Dashaputre from ISER Pune. So I am Simran, your PMRF teaching assistant. So I'm continuing with the week 6 lecture, which is on aldol and related reactions. So if you guys have any doubt regarding my previous videos, please ask me so that we can take up your questions. So anyone has any doubt regarding my previous videos?
no, ma'am.
Okay. So shall I proceed with this week 6 lecture?
Yes, ma'am.
Okay. So I have already discussed about the enols and enolates last week, right? So guys, now we will apply that knowledge of enols and enolates to these particular aldol and related reactions to do some questions based on that. All right. So the problem one which I have given is for the sequence of reactions shown below, which is the four options amongst these which is correct, right? You have to see now the reaction which is occurring in this sequence and have to answer according to that amongst these which is right. Okay, so coming to the first option, they are saying that compound A is a lithium enolate. They are telling about this compound A, right? So they are telling that it is a lithium enolate. So I have told you that in the previous lecture that if you have some ketone based compound in the system, then if you treat it with LDA, right? LDA is a non-nucleophilic base, right? So if you treat it with that, then you generate a lithium enolate. How? Because LDA has a counter ion, which is the lithium, right? So the enolate which is getting generated there is the lithium enolate, right? Because at the O minus after conjugation, right, this O minus have the counter anion of lithium. So here they are asking that compound A is the lithium enolate. So now you have to look at it carefully and have to see that here in this reaction, zinc is getting inserted in between this CBr bond because Br is a leaving group as you all know. This is a kind of Reformitsky enolate which is getting generated here, right? So what happens here is zinc first of all donates its electron to this carbon, and this carbon then release this Br, which in turn complex again with this zinc. So a Reformatsky enolate is getting generated here over the alpha haloester, right? So whenever you have this kind of system and you are inserting zinc in it, it will give the electron towards this carbon, and then this carbon leaves this Br out, which in turn again complexes with zinc to form a Reformatsky enolate, that is a C zinc Br bond, right? So this kind of enolate is getting generated here. So is this a lithium enolate?
No, ma'am.
Right. So it is not a lithium enolate. Why? Because here the enolate generation, here see what happens here, this negative charge is getting generated, right? Because this charge is getting generated how? Because zinc is now inserted in between this CBr bond. Zinc, as you know, is a metal, electropositive in nature, right? So it will generate a negative charge here, a negative charge here. So which is now conjugated between this carbonyl bond. So now this enolate is stabilized and is known as Reformatsky enolate rather than the lithium enolate, because it is not this anion is not stabilized by a counter anion which is lithium, right? It doesn't have a counter ion which is lithium. So whenever you have an LDA kind of situation and the anion which is getting generated, which is delocalized, having the lithium ion as the counter ion, then only you can say that it is a lithium enolate. Okay. Now here we have the CZN enolate, which is also known as Reformitsky enolate. So it is clear that that the option one is not the right answer. Now coming to the options B, the second step is the benzylic acid rearrangement. The second step. This is the first step which we have discussed. Now they are telling that this second step is a benzylic acid rearrangement. See what happens when you treat it with this, like this C zinc Br reformetsky enolate is getting generated for this compound, right? So now this CBr bond, zinc is getting inserted. So after that, this anion, what it will do, it will now behaves like this. See, here negative charge is getting generated, right? And then it get delocalized with this delocalization is okay, but now this anion will attack on this particular aldehyde, and this kind of intermediate is getting generated here, right? And you have seen here that the second step is water. They have treated it with the water. So water is here is nothing but the proton source, right? So when you have this O minus oxyanion is the generation, then when you treat it with water, what happens? This will abstract a proton from this water, and it will give you this alcohol. Okay. So is this mechanism clear to all of you? How this anion is getting generated and how it is attacking on this particular aldehyde?
Clear, ma'am.
Okay. So now coming back to the question. So second option was the second step is the benzylic acid rearrangement. Guys, what a benzylic acid rearrangement is, now we have to look at it. This is the benzylic acid rearrangement. This is the substrate. Here, first of all, when we treat it with the OH minus, either a KOH, either a NaOH kind of base, if you treat it with like that, what happens? One of the ketone is now substituted with this OH, right? And then this migration of phenyl ring is taking place here, and after that, this kind of species is getting generated. Okay, this is how benzylic acid rearrangement works. Okay, it's a name reaction widely used. So this is how it will work. Now tell me, is this the mechanism which is matching with the previous one which I have showed to you, all of you? Is this the benzylic acid rearrangement? Is there any migration which is taking place? Is there any benzyl which is the reacting species? Is my question clear to all of you? See, what I am asking here is that they are telling that this particular mechanism which is occurring in the second step, right? They are telling that it is the best benzylic acid rearrangement. Now we have looked at the mechanism of benzylic acid rearrangement. Here it is also known as the benzyl. See, this 1,2-diketone species is the reacting species in the benzylic acid rearrangement. We start with this kind of species. When you treat it with a strong base, either a KOH or a NaOH base, then it will attack on one of the carbonyl group, right? And then this tetrahedral intermediate is getting generated. Now this phenyl ring is getting migrated over here, and this kind of intermediate is getting generated here. An acid and alpha alcohol acid is getting generated. So can you say that this kind of reaction or mechanism is true for this particular mechanism which I have shown to you, all of you? Can you say that it is a benzylic acid rearrangement?
Yes, ma'am.
How? Is there any migration of phenyl ring or something happening here? Is there any migration happening? See, what you understand about migration is that one species, which is like this, just focus on this carbon. If it has a phenyl group, and this phenyl group is migrating to adjacent carbon, either there, either here, right? Then you will say that there is a migration in this particular system, because this migration is occurring from the adjacent carbon to this carbon 1 and carbon 2, right? Is there any migration taking place in this mechanism? See carefully and then tell me. See here, no migration is taking place, right? So what happens here is, benzylic acid rearrangement, for a benzylic acid rearrangement to takes place, you first have to have this benzyl as the reactant, okay? And we have an reformetsky enolate as a reactant, okay? So this kind of scenario is now here vanishes, because there is no 1,2 diketone system which is present here. Both the reacting species, is there any 1,2 diketone species which is present? Guys, at least tell me that. Okay, there is no 1,2 diketone species which is there in the reactant, and there is no such kind of condition which is implying here of the migrations. So this is not the benzylic acid rearrangement which we are talking about in the second step, okay? So the compound, so the answer B is also not the particular answer which we needed, so it is not correct, both of the statements. Now coming to the third statement, compound B has two aromatic rings. So compound B, I have showed you all how compound A is getting formed. This is A. And how compound B is getting formed. This is B. Is this mechanism clear to all of you? Just first tell me that. Guys, please respond, because if you are responding wrong answer, it's okay, okay? Because you are here to learn, right? So don't feel ashamed of your wrong answer. Just have a guess, just tell me. I will appreciate your effort, no doubt, okay? So now, is this mechanism clear to all of you? How A is getting formed in this reaction and how B is getting formed in this reaction?
Clear, ma'am.
Okay, thank you. So, if it is clear, then tell me that compound B has two aromatic rings. They are telling in compound A has two aromatic rings. I have showed you that this is the compound A, right? In this case, this is the compound A. So, is there any two aromatic ring which is present in the compound A? No, right? There is only one aromatic ring which is present, that is the benzene ring. Now they are saying that, is there any two aromatic ring present in the compound B? Is it correct?
Yes, ma'am.
Yeah. So which is the correct answer amongst all the four? Third one is the correct, right? So this is how you have to see all the things and then have to answer and then have to think about it. Okay. So if you are giving a wrong answer, then don't feel ashamed of that. You are here to learn. I'm here to teach. Okay. So ask me whenever you feel that you doesn't understand anything. I will happy to answer all your questions. Okay. So I will. Should I proceed to problem two?
Yes, ma'am.
Okay. So here they are asking which of the following aldehydes will undergo a Canizarro reaction. So before knowing what are the aldehyde which is going to give you a Canizarro reaction, first we have to know what is a Canizarro reaction. Okay. So now in the Canizarro reaction, what happens? The first thing to have in a Canizarro reaction is you should have a aldehyde or a ketone which doesn't have an alpha hydrogen within it. Okay, for the Canizarro reaction to takes place, the first very much essential requirement is that your aldehyde or ketone doesn't have alpha hydrogens. Okay, alpha hydrogens like in this alpha position, it doesn't have an hydrogen. Okay, so if it doesn't have an hydrogen, how now NaOH will react with it? It doesn't have a chance to abstract the alpha hydrogen, which is acidic, right? So what happens? What now base will do? Base will either act as a nucleophile or a base, right? I have told about you this to you. So now, if it is not acting as a base because it is not abstracting an hydrogen because there is no alpha hydrogens, just let it assume it as a pH, as an aromatic ring. If this R is an aromatic ring, okay, this benzene ring, then if is there any alpha hydrogen which is present in the system? No, because in the benzene ring there is no sp3 hybridized proton which is present, right? And here also this H will not, obviously base will not abstract this hydrogen, all right? So there is no alpha hydrogen which is present in this particular system for the base to abstract it. Okay, so there is no acidic proton. So for the Canizaro reaction to take place, this reacting species or the reactant shouldn't have an alpha hydrogen within it. Okay, so now base will now doesn't act like a base; it will act as a nucleophile because there is no acidic proton to abstract it. Okay, so now it will act as a nucleophile. It will attack on the carbonyl carbon, and then this tetrahedral intermediate is getting formed, right? So now this base again will abstract this proton. Now this OH is getting substituted here, right? So this OH hydrogen is also abstracting by the base. Now this kind of dioxyanion tetrahedral intermediate is getting formed, right? And now another molecule of this reactant, what it will do, now this hydrogen is very much, now it is not acidic. What happens here is this oxyanion, this O minus comes down and this hydrogen will leave out as in hydride. As in hydride, not a hydrogen ion, it will leave as in hydride. H minus, this is an hydride. So now this H minus will attack on this carbonyl carbon, and then again this kind of tetrahedral intermediate is taking place, and this 3 is now converted to 5. So after abstracting protons from the proton source, they will now get you an acid and an alcohol. So this is how a Canizaro reaction works. You will turn out to have an acid and an alcohol of the same species in the system. Okay. Just look at this mechanism. I will explain it to you all again because I know it is bit tricky. So see what happens here. For the Canizaro reaction to take place, you don't have to have a alpha hydrogen in the system. So if you treat this R as in pH, that is the benzene ring, okay? So now there is no alpha hydrogen which is present in the system, and for the base now it cannot extract this kind of hydrogen because it's now sp2. This is not acidic. So enolate formation is now not taking place here. Is it right? Have you understand how this much? How an enolate formation is not taking place in this particular system by the base because there is no alpha hydrogen which is present here to base to abstract it, and then only if the abstraction takes place, only then this negative chain is anion is getting generated and which is delocalized to get you enolate, right? This is how we have explained in the aldol condensation. What happens, base will abstract the alpha hydrogen, and then this alpha hydrogen will form an enolate, and then it will attack to another aldehyde or ketone to give you alpha beta unsaturated ketones, right? This is what aldol condensation is. Okay. But when you have a Canizaro reaction, it is different from aldol condensation in the respect that it doesn't have alpha hydrogens in the system. So if you have an alpha hydrogen, you will end up like an aldol condensation because it is the NaOH or KOH only. It will abstract the hydrogen and it will form an enolate. in aldol condensation if you have alpha hydrogen. But in the Canizaro reaction, alpha hydrogen is not there. That is why it can't be able to form this anion, and the enolate generation is not taking place here. So this OH minus will rather behave as a nucleophile rather than the base. Okay, it will behave as a nucleophile. So OH minus then attack on this particular carbonyl carbon, and this kind of tetrahedral intermediate is getting formed. And after that, this base again abstract the proton from this OH, leading to the formation of this oxyanion, dianion. Okay, one of the oxyanion now cleaves, and this carbonyl bond is getting formed. Now this hydrogen is getting leaved as an hydride. Okay, which again on the similar substrate will form and this kind of tetrahedral intermediate, and now this acid and alcohol kind of thing is getting formed after the proton abstraction. Is it this mechanism is clear to all of you, or I have to explain it again? Just tell me, guys. Have you understood how Canizaro reaction works?
Yes, ma'am.
Okay. So if you understand this, then coming back to the question, they are asking which of the aldehydes will undergo a Canizaro reaction. Okay, you have to just identify which of the aldehyde will give you a Canizaro reaction. Now you have this formaldehyde, you have this benzaldehyde, this isopropyl aldehyde. So now tell me, amongst these three, does any of them have the alpha hydrogen? Just see whether it have the alpha hydrogen or not, and your answer is there, because they are only asking you that which aldehyde will not give you will give you the Canizaro reaction. So this is the formaldehyde, guys. Does it have the alpha hydrogen? Are you understanding the thing of the alpha hydrogen? See, this doesn't have the alpha carbon because there is only hydrogen which is present, right? So if the alpha, this is methyl. See, if this is methyl instead of the hydrogen, if this is methyl, then it has a alpha carbon, right? And it also has the alpha hydrogen because this carbon is attached to three hydrogens. And now this base can abstract the hydrogen from this side, and an anion can get generated which delocalize to form an elolate, and which happens in aldol condensation only. Okay, so now they are asking that in the Canizaro reaction, which aldehyde will give you that? Only that aldehydes will give you the Canizaro reaction, which doesn't have the alpha hydrogen in it. Okay. So so just tell me that this HCHO, this formaldehyde, does it have an alpha hydrogen within it? See, it doesn't have an alpha hydrogen because it doesn't have an alpha carbon to have hydrogen. Does it have alpha carbon? No, it doesn't have alpha carbon because on both the side it have only hydrogens. So there is no alpha hydrogen which is present in the system. It doesn't have the alpha carbon instead. Okay, so it is not. It will give you the Canizaro reaction. Now coming to the benzaldehyde. This is the case which I have explained you by the mechanism. If you treat it with if you treat it like pH, this R, then it doesn't have the alpha hydrogen we have discussed, right? So if this phenyl ring is on one side, see, this is the benzene ring. If it is the benzene ring, and this is the carbonyl group. Okay. Okay, now just tell me that if this has the alpha hydrogen. See, guys, please respond because I am unable to understand whether you are getting that thing of alpha hydrogen or not. If it is not clear, just tell me. I will answer you perfectly then. Okay, so this benzaldehyde doesn't have an alpha hydrogen because there is a quaternary carbon and there is a hydrogen. So there is no alpha carbon on this side, and this carbon doesn't have the hydrogen because it is sp2 hybridized, it is a quaternary carbon. Okay, so there is no alpha hydrogen in this system, so that is why it is also able to give you the Canizarro reaction. Coming to this particular thing, now this carbon is connected to three methyl groups, but we have studied that this aldehyde, this carbon, this for this aldehyde, this carbon of CH3CH3CH3 is the alpha carbon, and this methyl carbon is the beta carbon. So that is why we have to have the condition of alpha hydrogen. Now here, this carbon doesn't have an alpha hydrogen because it is connected in turn of three methyl groups, right? So how the valency of carbon is 4, we all know. So this is the 3 methyl which is connected here, and this is the aldehyde. So this alpha carbon doesn't have the hydrogen, so that is why it is also able to give you the Canizarro reaction. So all of these is able to give you the Canizarro reaction. So the correct answer is all of the above. How? Because for the Canizarro reaction, you have to have a condition that you don't have alpha hydrogen in the reacting species. Okay, in the substrate, you doesn't have the alpha hydrogen. So all of these aldehyde will successfully accomplish the requirement of not having alpha hydrogen at the alpha carbon. Okay, so that is why these all can give you a Canizarro reaction. Now coming to problem 3. So problem 3 gives you that in the reaction the products X and Y are respectively what? So now it is the implementation of Canizaro reaction only. So you have to figure it out what is X and what is Y here. Okay. So just tell me, is there any alpha hydrogen present in this system for this NaOH which is concentrated a strong base to abstract hydrogen? Is it able to act as a base in these two reacting species? Does it have any alpha hydrogen which is attached to these aldehydes? Just make a guess, guys. It's important to respond, right?
Once again, repeat, ma'am.
Huh. See, what I'm asking here is, see, this base NaOH, now they are asking that products X and Y would be what? So I have just told you about the Canizaro reaction, right? So just think about it, that base, what it can do. It will either abstract the alpha hydrogen as a base or either will act as a nucleophile, right? So, for acting as a base, thus these reactants have the alpha hydrogens present in them. I'm asking that. Does the formaldehyde have any alpha hydrogen?
No, ma'am.
Yeah, good. No. Now, this a kind of substituted benzaldehyde, does it have a alpha hydrogen?
No, ma'am.
No. Very good. So these two species doesn't have any alpha hydrogen. Okay, so that is why this base cannot act as a base, standard base to abstract the alpha hydrogen. So it cannot act as that. So now what option will this base have to act as a nucleophile only, right? It can't
Yes,
act as a
ma'am.
base, so it will act as a nucleophile. So now, if it act as a nucleophile, it is similar that of this Canizaro reaction. It is the implementation of the Canizaro reaction. Now, what happens here? Someone is joining. See what happens here. First of all, you have this formaldehyde in the system. Okay. So now tell me, this formaldehyde or this aldehyde, which is more electrophilic in nature? This formaldehyde is more electrophilic in nature. How? Because it is connected to an hydrogen and it is connected to a methyl, right? Sorry, a phenyl. It is in conjugation, this system is in conjugation with this carbonyl group, right? This is in conjugation between this carbonyl group. So there is a partial double bond character which we have already talked about in this carbon and this sp2 hybridized carbon. There is a partial double bond character, so which reduces the electrophilic nature of this particular aldehyde. That is why this formaldehyde is more electrophilic in nature, because it is not in the conjugation with anything, because here is only a hydrogen which is present subsequently. So, first of all, base will attack on this formaldehyde because it is more electrophilic in nature, and base, as a nucleophile, it will attack towards the more electrophilic carbonyl carbon. Okay. So now it will attack on this. This tetrahedral intermediate is getting formed with the this OH. Now this oxyanion, this O minus will come down, and now this hydrogen will leave as an hydride, which I have told you previously in the Canizarro mechanism, that this hydrogen is now leaving as an hydride. It will attack on this particular carbonyl carbon of the reacting species which is here, right? So it will attack on this carbonyl carbon of this paramethoxybenzaldehyde, and then this O minus is getting generated here, right? I have skipped a step because I have showed you in the Canizarro mechanism this O minus is getting generated, and after the protons abstraction from the proton source, and this alcohol and this formic acid is getting generated here. So now tell me, what are the X and Y amongst these four options? Which is correct option?
Fourth option, ma'am.
Fourth option. Right. Fourth option is the correct one. Okay. So fourth option is the correct one. So have you understand how a Canizaro reaction works? You will end up with an acid and subsequently an alcohol in the system. Now you have to figure it out which is being an acid and which species will act as a alcohol, depending on the electrophilicity of the carbonyl carbon. Only first of all, the electrophilicity of the carbonyl carbon uh, plays a role here, and then this hydride transfer will take place on the another carbonyl carbon, and you will end up having an acid and an alcohol in the system. Okay, this is how Canizaro reaction works. For this reaction to work, you have to have doesn't have an alpha hydrogen in the system. Okay, is this much clear to all of you?
Clear, ma'am.
Yeah, very good. So I will proceed to problem 4. So now they are asking, identify the final product of the following Reformetsky reaction. Please guys join on time. It is very difficult for me now. So we were at the problem 4. So now they are asking the final product of this Reformetsky reaction. So here, see what happens here is, now this Reformetsky enolate is there, right? I've told you that this zinc is a metal, it is electropositive in nature. So the carbon which is connected to this particular ZnBr species is nucleophilic in nature. So it have a carbon at this position. So a partial positive charge is here and a partial negative charge is there. Okay. So now they are telling us to treat it with this species. So what happens here is, this anion will attack on this particular aldehyde, benzaldehyde, and this tetrahedral species is getting generated. Now what happens here, instead of abstracting a proton from the proton source, what it will do, as they have done the acid workup, Workup means that they have also provided you the proton source. Okay. So this oxyanion can either abstract a proton and it will turn into an OH, or either it can do another reaction with this COET ester group, because of the formation of this five membered favorable species, right? Because you have a nucleophile here and an electrophile in the system, and it is intramolecularly present. As you know, guys, that this intramolecular reaction are very much faster than the intermolecular reaction. Sometimes what happens there is that the intramolecular reaction works for the same species, but the intermolecular reaction can be so much sluggish. Okay, in fact, it cannot work in even. So you have an electrophile here and a nucleophile in the system, which is present intramolecularly, and you can end up by attacking of this oxyanion on this particular carbonyl carbon. If it doesn't have the COAT group in the system, what happens? That it will abstract this oxyanion will abstract a proton from the proton source, and it will end up there only. Okay. So what you have here is that this COAT is not there, and but only this kind of system is there with OH. Okay, but now here you have the COET, and you know that OET, this ethoxide, is a very good leaving group. Okay, so this oxyanion will attack on this carbonyl carbon, and it goes up. When it comes down, it will leave this OET. This OET knocked out like this. Now it will come and it will knock out this ethoxide, giving you a five membered species. So this is a lactone which is forming here. Okay. So because of this, the favorable five membered species formation, which is occurring intramolecularly very faster, that is why you are ending up with this kind of species rather than ending up with this kind of species. Okay. Is this mechanism clear to all of you? Why it is happening? If you have any doubt, please ask me.
Once again, repeat, ma'am.
Okay. See, in the question, they are asking the final product of the Reformatsky reaction. They are saying that we have done the acid workup. Acid workup means that they have given you proton source here. So if you have an oxyanion in the system formed, then it will convert into the alcohol form because of this proton source which is here in the system. Okay. So now they are treating this zinc Br, it is enolate of this Reformatsky with this particular benzaldehyde. Okay. So as I have told you that this zinc is electropositive in nature because of it is a metal. So the carbon which is connected in the CZnBr bond is nucleophilic in nature. So the air is a there is a anion which is getting generated on this particular carbon, and which then attack to this particular aldehyde, giving this kind of species. This O minus pH is getting here, and this kind of species is there. Okay. So now this oxyanion, as they have told you, there is an acid workup. So it will either it will abstract a proton source, and this OH can get formed. Okay, either this possibility is there, or the possibility here is also there that this oxyanion can attack on this carbonyl carbon of this COET, this ester group, and this ethoxide leaves out to form this five membered species. How five membered? One, this two, this three, this four, and this five. This carbon is five. Okay. So this five membered species is getting formed here, and now this O minus will come down and this ethoxide knockout to give you this kind of lactone species. Okay. This happens because it is present intramolecularly, and you have an nucleophile here and electrophile here. That is why you will end up with having a five membered species rather than the alcohol. Is it clear now, or you have any doubt?
Clear, ma'am.
So The correct option will be what?
Third option, ma'am.
Very good. So the third option is the correct one. So now coming to the problem 5. It is a very easy problem, guys. So just have your minds on it. So see, here what they are asking is, what will be the major product of the following alkylation reaction? So now here your N-butyl lithium is there. So N-butyl lithium is also a base. It will abstract acidic proton from your system. And then they have treated it with dry THF, and the second step is they have treated it with the RBR. So now from the first step you have to look out that which of the proton is so much acidic that it will abstract it. So now butyl lithium is a base, so it will abstract a proton from here, and then that proton, that anion which is getting formed, will attack on this RBR. Okay, this is the second step. Don't worry about it. Just worry about first step only. That what is happening here. So N-butyl lithium is a base, no doubt. So now which proton is so much acidic for it to abstract? Either it will be this, it will be this. So which proton it can abstract? See, if it abstract this proton from the left side, then the anion which is getting generated here is not delocalized, because if you put it in the situation of this delocalization, then there is no double bond here to delocalize with this particular anion which is getting formed, right? But if you abstract a proton here, this carbon ion is getting generated at this carbon, and as you can see, it can go here, and delocalization is there. So there is a delocalization present when you are abstracting an anion from this position, the proton from this position, sorry. So which is favorable? The delocalized stable carboxy anion which is forming here, or this particular anion from left hand side which is forming? So which is more stable? Any guesses?
Right hand side, ma'am.
Very good. So the right hand side proton, which is present here, is much more stable due to the conjugation, and that is why the N-butyl lithium will abstract this proton instead of this, because there is no delocalization and there is no stabilization of this carbon ion which is getting formed. So what happens here when you treat it with I have written as LDA, it is butyl lithium. Okay, it is butyl lithium. So when you treat it with butyl lithium, then what happens here is this anion is getting generated because this proton they have abstracted, and this anion is now in conjugation with this double bond. So this is how it is getting stabilized. So this anion now attack, after coming back, it will it will attack on this R bond, and Br knocked out, because Br is a minus species, right? This is nucleophilic in nature, and this is the electrophile which is present here, this R. That is why this anion being nucleophile attack on the electrophile, and this R is getting substituted here. So this kind of alkylation is getting placed. Okay. So now which is the correct option amongst these?
Option A, ma'am.
Very good, option. So is this much clear to all of you how it is happening? How, why this is the only proton which is abstracting by the butyl lithium, not this proton is abstracting?
Clear, ma'am.
Very good. So coming to the problem 6, see, this is also a very straightforward question. You don't have to do anything with it. See, they are asking identify the major product of the following reaction. So now, first of all, they have treated it with LDA again, THF. So now there is two possibility. Which of the proton will get? There is only one possibility actually, because this proton is present here and this hydrogen is here. Now, does this carbon have any hydrogen? No, because there is also a substituent which is already here. It is the blocked position. So there is no proton which is present here. So what you can say, that there is only these protons which are present near the carbonyl group or in the conjugation. So this is the acidic proton. Why? Because after removal of the proton from this side, you can have the delocalization, which is stabilized like that. There is no proton which is present here. Carbon 4 valency is satisfied, so there is no need of 5, right? So there is no proton which is present here. That is why they have abstracted LD and abstracted this proton. And now the main question comes, right? Now just tell me, iodine is the good leaving group, iodide, sorry, or the chloride is the good leaving group?
Iodine is good living group, no?
Very good. So the iodide is a good living group. How? Because when you go from the period, see how it is going from the group. Sorry, this chlorine, chlorine, bromine, iodine. When you are going down, the size is getting increased, right? So the negative charge which is present on this particular leaving group after leaving, either I minus or ICl minus will leave. Okay, so the negative charge is very much stabilized because of the large size of this iodine, and that is why it is a good leaving group than chlorine. Because as you know, iodine is in bigger size than chlorine, right? So it will behave as a good leaving group. So now this anion will attack on this particular carbon, this side, and this iodide leaves. So this kind of species is getting generated. So now, which is the correct option?
Option C, ma'am.
Very good. Option C is the correct option. So now, coming to the problems here. So now, see here, they are asking the major product form in the following reaction. Is there anyone? Okay. So the major product. They are treating it with KOH base and the methanol, which is a proton source here. Okay. So now, when you have a base in the system, what it will do, either it will abstract the alpha hydrogen or it will add as a nucleophile. So this system, as you know, have the alpha hydrogens. This side also it have hydrogens. It will, this side also it will have the alpha hydrogen, and also same with this side. So now, as you know, LDA is an in the case of LDA, what you end up is with the kinetic enolate. I have talked about it right previously. Kinetic enolate means that you abstract the proton from the less hindered side. Okay, because LDA is itself very bulky base. But is it a bulky base KOH or NaOH? Is it a bulky base? No, because potassium and sodium is a small size species, right? LDA is itself a very big, is a very bulky base. So now there is a competition between the removal of protons, because here also you have hydrogen, here also you have hydrogen. So which hydrogen, as the secondary carbon hydrogen or the primary carbon hydrogen will leave out? So now you will end up to have a kind thermodynamic enolate in this case. What is means by the thermodynamic enolate? The thermodynamic enolate is this, when it is more stabilized. When you abstract the proton from a like more hindered site. Okay. So this anion is getting generated here if you abstract a proton from the more hindered site. This is the more secondary carbon is more hindered than primary, right? So that is why you end up with the more stable carbon anion, which is thermodynamically stable, because in this case you have a small base. If in this case you have LDA, just suppose if you have LDA instead of KOH, then which proton will it will abstract? Either this primary proton or these primary protons. It will abstract these protons only. It doesn't go for the sterically for the sterically more hindered protons. All right. But in the case of KOH, because it is a small base, strong base, so it will go for the more thermodynamically stable enolate. Is it clear? Or you guys have any doubt?
Once again, repeat, ma'am.
Okay. See, in the case of LDA, lithium diisopropylamide, okay, it is it is itself is a very bulky base, as I have told you guys already, right? In this case, see, LDA is abstracting proton from this side, which is less hindered, not from the this side. This also have the hydrogen, right? But it is not abstracting this kind of hydrogen. Why? Because LDA is sterically hindered base, and that is why it prefers to form the kinetic enolate. Kinetic enolate means that the enolate which is getting generated from the less hindered side. So it is the less hindered side. It is the more hindered side because OET also present. So it will abstract the proton from the less hindered side. But in the case of KOH, NaOH, it is the strong basis, but it is not bulky basis. Okay, it is not the bulky base, so that is why it is go for the thermodynamic enolate formation rather than the kinetic enolate. So for the formation of thermodynamic enolate, it will form when you abstract the protons from the more hindered side. So now here, this is the hindered side, this is the hindered side, and at this particular carbon there is no hydrogen which is present. Okay, but here you have the hydrogen. So this is the side which is more hindered because this is the primary carbon and this is also the primary carbon, but this is the secondary carbon. Okay, so now these have hydrogen, and if you abstract the proton from here, you will end up with a more stable thermodynamic unit. That is why KOH will abstract proton from the secondary carbon to form a thermodynamic unit because it is not sterically hindered. Is it clear now?
Yes, ma'am.
Okay. So if it is clear, then you can think of this kind of anion is getting generated in your system. And I have told you that if you have an anion generated in the system, it will intramolecularly attack on the electrophile, because as it is a nucleophile here, so now it will intramolecularly attack on this particular carbonyl carbon, giving you a six membered ring formation. How? This is the one carbon, this is the two carbon, this is the three carbon, this is the four carbon, this is fifth, and this is sixth carbon. So this six membered ring formation is taking place here, and what you have here is the oxyanion. This is the O minus. Now in this system you have also methanol. So what it will do? It will protodent this oxyanion and form an OH. Okay. Now after the dehydration, now here you can say that this have an hydrogen. So now dehydration can take place, and this kind of alpha beta unsaturated ketone is getting formed. Why it is not ending up at this? Because as you know that alpha beta unsaturated ketones are more stable, right? Because of the conjugation here, that is why dehydration is taking place to give you this alpha beta unsaturated ketones. Okay, so this is what you will end up as a product. Is this much clear to all of you?
Yes, ma'am.
Okay, so which is the correct answer among these?
Third option, ma'am.
Good, option C will be the correct answer. Moving towards the problem 8. Okay. So moving towards the problem 8. See, what happens here? They are asking that predict the major product from the following reaction. It is also similar. See, I have taken all the similar kind of questions so that you will have a impact on that, right? You will have an impression that yes, if zinc is present in the system, it will insert between CVR bond, and now how it will react on further, right? You just have an impression on in the mind that yes, this kind of substrate act like this. So that is why I have taken the related questions only, not the very vast questions. So that just if you have gone to all the problems, then you will understand that yes, these problems are very similar and very straightforward also. So, in this case, what happens here? That they are asking that this when this aldehyde in the system and this dibromo species is also there. So you have to insert zinc in between. So now just tell me that this carbon CBr and this sp2 hybridized carbon Br, in which of the following zinc will get inserted? The primary one or the this particular sp2 hybridized carbon? Is it the sp3 hybridized? No. So is generating a negative charge here is more beneficial, or generating a negative charge on this particular carbon of sp2 alkene is stable? Which is stable?
sp2 alkane is less stable, ma'am.
Very good. sp2 alkene is very less stable because it is not stabilized. The negative charge on sp2 hybridized carbon is very, very unstable. Okay. So here, if you have this kind of negative charge generated, then it will delocalize with this particular thing. But in this case, in sp2 anion is very unstable. That is why zinc will insert in the CBr bond of this primary carbon. So after insertion of this Z and Br, what happens? They have treated it with this aldehyde. So this aldehyde. So this anion, again, this carbon is nucleophilic in nature. So now this will attack on this carbonyl carbon, giving you a conjugated system. And now there is no another functionality which is present. Now this O minus, if this will form, there is no other functionality which will act as a electrophile here. That is why it is arrested here, and that is why you will end up this product only. Okay. If there is a carbonyl group present in the system and the formation of 5 or 6 membered ring is happening, then you will end up with a 6 membered or 5 membered ring, and you will have another set of reactions. But here there is no other functionality, that is why you are ending up with this OH only. Is it clear?
Yes, ma'am.
Okay. So which is the correct answer among these?
First option, ma'am.
First option will be the correct. So now coming to the last problem of this session, problem 9. This is the last question for this session. So they are asking what is the major product formed in the given reaction. Again the similar one, concentrated NaOH. They are treating this ketone to concentrated NaOH. What it will do, what a base can do, either it will act as a base, or either it will act as a nucleophile. So thus this system has the alpha hydrogen present in this particular case.
Yes, ma'am.
Yes, very good. Be confident on your answer. You are answering correctly, because you have to figure out that there are two alpha carbon which is present. This carbon and this carbon. Respect to the ketone, you have to see alpha, beta, gamma, delta, right? So this is the alpha carbon on both the sides. So is this carbon having any hydrogen? No, because it's the quaternary carbon. Is this carbon having any hydrogens here? Yes, there is two hydrogen which is present because it is sp3 hybridized, right? So that is why you will end up having a base and an ion in the system which is getting generated, and it is also an enolate which is stabilized, right? So now this anion will, as you have only one species in the system, only one reactant, so it can react with itself as well, right? If you doesn't have any other reactant in the system, what a single reactant will do, it will react with itself. You doesn't have any one, only one mole of this particular thing, right? You doesn't have only one molecule of this reactant. If you add something, like if I had any ketone in the system, see, so can you say that I have added only one unit of this ketone? No, because when you add a thing, then there is number of molecules which is present in the system. Okay, so now there is number of this kind of reactants which is present. So that is why now this anion will attack on the reactant itself, and this carbonyl carbon will end up with having a oxyanion. So now this oxyanion will form here. So it will abstract proton from the proton source, and now you will end up as an OH. Either you can write it like this or you cannot. Okay, both of them are same. So this OH is now you have this hydrogen in the system. In the similar case as the previous question, I told you that if there is possibility of generation of alpha beta unsaturated ketone, system will prefer that because of the more stable conjugation which is present between alpha beta unsaturation. There is no conjugation between this particular OH and carbonyl which is present here. That is why dehydration step is taking place to give you a more substituted, sorry, a more stable alpha beta unsaturated ketone. Here also, the same case is there. After forming this oxygen ion, it will abstract a proton from the proton source, forming an OH here, and you have an hydrogen here, and also there is no conjugation between here. It is a conjugation, no doubt. But if you have this OH here and H here, if you leave the system like this only, does this carbonyl is stabilized by this kind of conjugation here? No. So this dehydration step takes place, and now you have an alpha beta unsaturated ketone on both the side which is resonance stabilized. Okay, so you will end up with this kind of product rather than this kind of product. Is it clear to all of you? Any doubts?
Ma'am,
Yes.
so the purpose of dehydration takes place is stabilization of the product, ma'am.
Yes, the stabilization of product. Because see, when there is no dehydration, see, it is also the thing that if you heat in the system, then the dehydration takes place. If you add something like PTO5, then dehydration takes place because they are dehydrating agents. But the system also undergo dehydration when the product have more stability than the previous one. So if you look at this particular product, if you ended up like that, there is no further conjugation which is coming from this carbonyl, so there is no that much stabilization. If you do the dehydration, then you will end up with that this kind of alkene, and now there is a alpha beta unsaturation on both the sides. So now this system is much more stabilized than the previous one. That is why their dehydration is a taking place. So this is the driving force of that particular dehydration. Okay, it is not necessary that the driving force is
Okay, ma'am.
always this. It can also be if you can put a dehydrating agent in the system, dehydration takes place. If you reflux it at high heat, heating it, then also dehydration will take place. It depends. But in this system, the driving force is the stability of the product. Okay.
Okay, ma'am. Thank you, ma'am.
Okay. So the correct option will be option. So the correct option will be option one. One, right? One or four. Which option is correct?
Four, ma'am.
Yeah. Option 4, right? So it is the correct option now. So this is the last question of this particular session. So now, guys, I hope you have the mindset of doing the questions or to approaching the questions. Now you got it how we will have to deal the particular situation. So with that, I'm just closing this session. I hope these answers are clear to all of you. If you have any doubt regarding any of these questions or any of the previous assignments, then please let me know in the chat box or in the next session we will take. So I hope it is clear to all of you. Thank you so much for attending my class. Thank you so much for patient listening, and thank you so much for responding. Okay, it is very essential for a teacher to get a response so that he will know, or he or she will know that how we have to explain the things out. Okay, so thank you so much. I'm ending up this session.